Okay, what we're going to do here is we're going to make a video about water. Okay, you know a lot about it, and after today, hopefully you know a lot more. So let's start at the basement level. Let's start as easy as it gets. What is the formula for water? Okay, you guys all know, even though you're only 8th graders, you guys all know that the formula for water is H2O. So what does that mean? That means water is a compound, and compound means more than one thing. So water is a compound of hydrogen and oxygen. So what are these two things, hydrogen and oxygen? Well, hydrogen is a gas, and it's very flammable. When I think of hydrogen, I think of this. I think of this big airship called the Hindenburg. Mr. Wiki knows his history better than I do, but I think this actually exploded in the U.S., like New Jersey or somewhere. And there were these metal lines that they were going to use to tie it to these ground moorings. And I believe that what they think is a spark ignited the hydrogen that filled the airship, and the whole thing caught on fire and basically just blew up. So hydrogen is a very flammable gas. And what do you know about oxygen? Well, you know that it's also a gas at room temperature, just like hydrogen is. And you know that we need it to live, so it's needed for, I'm just going to say us. It's needed for us. We humans need it to breathe. And oxygen is what we call an oxidizer. No surprise there. Oops, oxidizer. And what does oxidizer mean? An oxidizer is something that helps things burn. So when you put these two together, what do you get? You've got oxygen that helps things burn, and you've got hydrogen, which is very burnable. So if you mix hydrogen and oxygen, you can get quite an explosion. And isn't that weird? You've got these two gases that are very associated with burning, and when you put them together, what do you get? You get a liquid. You get water. And we don't think of water as flammable or, associated with burning. Probably not the best color to pick there. Anyway, so that's some physical science about water. What are some other things about water? Well, let's talk about its boiling point and its melting point. At regular conditions, water boils at 100 degrees Celsius, and it melts at 0 degrees Celsius. Those numbers are very easy to remember, 100 and 0. Why do I use Celsius? Well, like I said, because it's easier. I'm just curious, how many of you in this room know the boiling point and melting point of water in degrees Fahrenheit? I'm guessing that most of you don't know, even though you're Americans and you say your temperature's in Fahrenheit every day. Maybe this would be a good place to pause for a second and see who knows that. Okay, so boiling at 100 and melting at 0. I should probably also tell you, whoa, what happened there? I don't know what happened there, but anyway, I should also tell you that the boiling point can change. You can make water boil at a number a little bit above 100 or a little bit below 100. And you can also make water melt at a little bit above 0 or a little bit below 0. Or I guess even a lot. So how would you do that? How do you suppose you could make water without adding anything to it? How could you make water boil above or below 100 degrees? Maybe this is another good place to stop the video and take some guesses. Okay, so maybe you've heard of a pressure cooker before. Pressure cookers are these sealed saucepans or these sealed pots, and what they do is they put a very tight lid on whatever you're cooking, and it doesn't let the heat escape. So by keeping that heat in, you can make water, you can boil water at much higher than 100 degrees. So guess what it's like inside this container? Well, it's very hot, of course, but inside that container, there's a very high pressure. So if you increase the pressure, you can make water boil at a temperature above 100 degrees. So do you suppose if you have a high pressure and you can boil water at above 100 degrees Celsius, do you suppose that if you have low pressure that you can boil water below or some number less than 100 degrees Celsius? Well, yes, it is true. Take a look at this. I went to the Betty Crocker website. It's full of like recipes and stuff. And what it says, if you want to bake and cook at high altitudes, if you look, it says right here, it says, air pressure is lower, so foods take longer to bake. Temperatures and or bake times may need to be increased. Liquids evaporate faster, so amounts of blah, 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 blah. So basically what this is telling us is that if you have low pressure, you can boil water below 100 degrees. So why would someone buying a cake mix, why would they have to worry about that? Well, picture this. Let's say here you've got the Earth, and here you've got a layer of atmosphere around the Earth. This is greatly exaggerated, but let's go with it. So let's say that you are right here, and you've got one atmosphere of air pushing down on you from all directions. And that means right here, your water is going to boil at 100 degrees Celsius. Now, let's say we've got this imaginary mountain over here, and let's say you've got a house on top of this imaginary mountain, and you want to bake a cake. Well, how much atmosphere is pushing down on you? Well, there's only a little bit of atmosphere above you, so the answer is less atmosphere. So if you were going to bake a cake up here on the mountain, you would boil your water at some number less than 100 degrees Celsius. That's kind of weird stuff. A lot of you probably had not heard that before. So that brings me to something it looks a little scary, but I hope it's not too scary. This is called a phase diagram. Check this out. So if you were standing by the ocean, you've got one atmosphere of air above you. So right here is one atmosphere of air. We're only in Beaverton, we're only like 800 feet above the ocean level, so we pretty much have one atmosphere of air pushing down on us. And right here at a temperature of 0 degrees Celsius, that's basically freezing. At that temperature, right here is where you get the melting point of water. So water melts and freezes at 0. So the melting point is the same thing as the freezing point. Also, if we heat up that water, if we go over here and we want to turn it into a gas, if we want to go from a liquid to a gas, we heat it up how hot? We heat it up to 100 degrees Celsius. So under 1 atmosphere of air, if we heat water up to 100, we can get it to boil. So right here is the boiling point of water. So now let's talk about our person who's living on the mountain. Let's say they're living on the mountain, and let's say that their air pressure is somewhere right around here. This is imaginary, but let's go with it. So if your air pressure is here, where is this going to hit? It's going to hit right here, a little bit, just a little bit to the right of our original spot. So that means our water is going to boil, is going to melt at a little bit above 0, a couple degrees above 0. And up in the mountains, where is water going to boil? Water is going to boil at some number a little bit less than 100 degrees. So the pressure that the atmosphere pushes down on us or around us in all directions makes a difference on whether we have solid water, liquid water, or gaseous water. So maybe we should pause the video here and talk about maybe some quiz questions that we could ask about this diagram. Okay, what's next? The next thing I want to talk about are what I call the big three. And I'm talking about solid, liquid, and gas. I'm talking about the 3 states of matter. Now, as 8th graders, you might know something about other states of matter like plasmas or liquid crystals and some others. But for this class, we only care about solid, liquid, and gas. So to study this, I'm going to draw a nice big triangle. And remember, we're talking about water here. So I'm going to put solid here, liquid here, and gas here. First off, let's talk about these 3 states of matter. What do we have here? What is solid water like? Well, solid water, it's ice. That's kind of a no-brainer. And what does ice look like if you could get down submicroscopically? Ice looks like this. So here it is. Here's ice. If we could see the actual ice particles. Right here, this is one molecule of water. There's one hydrogen atom, there's another, and there's an oxygen, so it's H2O. And in ice, these water molecules hook together and they leave all these big open spaces. All those big open spaces, that's why ice floats. Ice is bigger than liquid water. So let me go back to my note sheet here. So ice is less dense than liquid. And that's because the particles are kind of spread out a little bit more. What's going on in liquid water? Well, let me show you that. So in a liquid water, you've got all these little particles just jumbling around all over the place. So that's what it's like in a liquid. So let's write this next to liquid. In a liquid, the particles are sliding around. Okay, and then finally, what are particles in gaseous water doing? Well, let's look at this. So right here, look at this. You've got this liquid water in the bottom, like a glass of water, and then up in the air, there's water particles just bouncing around all over the place. So in gaseous water, what's going on is your particles are flying around. So the air particles in this room that you're in right now, some of the air particles are flying around at over 1,000 miles an hour. So it's pretty lucky for us that they're not very heavier. That would probably hurt. Okay, so now what I want to do is I want to switch my focus to energy. Solids have the least amount of energy. That should make sense because we said that in a solid, the water particles were kind of locked together in rows and they couldn't move very much. And who's got the most energy? That would be gas. So if you had some kind of a container with gaseous water particles in it, they would be flying all over the place, bouncing off of each other maybe and hitting the walls of the container. They're just bouncing all over the place. And so liquids, they have energy that's in between. So solids have the least amount of energy, gases have the most, and liquids have, we'll call that medium amounts of energy. So can you go back and forth between these states? Yes, you can. You're familiar with this. If you have solid water, in other words, ice, and you add some energy to it, so if you add some energy, what do we call that? Well, if you turn into a liquid, we call that melting. Pretty easy. And then, what if we take a liquid and we remove some energy from it? So if we remove energy, oops, I misspelled energy. What the heck? If you remove energy from a liquid, what do we call that? Well, if it turns into a solid, we call that freezing. Nothing new there. Now, let's do this. What if you take a liquid and you add energy to it? So I'll just write add here. What do we call it? Well, if we do it slowly, we call it evaporation. And if we do it fast, we call it boiling. So adding energy to a liquid, you can get a gas. But if you remove energy from a gas, can you get a liquid back? Yeah, yep. What we call that condensation. Okay, so let's look around on the internet for an example of condensation. This isn't bad. Like everybody has taken a cold can of pop, or like look at this, a cold glass of water, and on the outside of the glass it forms all these little beads of liquid water. Well, no, water didn't leak through the glass. Water that was already in the air somehow coated the outside of the glass. So what happened there? Well, imagine being an air particle. You're a gaseous air particle and you're flying around. If you suddenly get cold, what are you going to turn into? You're going to turn into a liquid. And so there's going to be a drop of water there. Okay? So that's what happens with condensation. So let's look at the bottom here. Is it possible to go from a solid directly to a gas, if you add energy to a solid, can it turn into a gas? Whoa, what happened there? I don't know. But yes, you can go from a solid directly to a gas. Let me redraw this. So if we add energy to a solid and we get a gas, so I'll just write add energy here. If we add energy to a solid and get a gas, that's actually kind of a weird word that I'm betting you've never heard before. We call that sublimation. So sublimation, if you take an ice cube, a piece of solid water, a chunk of ice or something, and even if it doesn't melt first, even if you don't turn into a liquid first, if you come back later, it could be a little bit smaller. Why would it be a little bit smaller? Because some of those particles, if they had enough energy, they could just jump off into the air, and that would make the particles smaller. That would make the chunk of ice smaller. So we call that sublimation. Now, if it's possible to add energy and go from a solid to a gas, do you suppose it's possible to go from a gas back to a solid by removing energy? Why, yes, it is possible. And when you remove energy from a gas and you get a solid, we call that deposition. Can you think of an example in your life where you've seen deposition before? In just a second here, I'll show you one. Okay, so take a look at these pictures. You've seen frost before. Frost happens when? Frost doesn't happen when it snows. No, you don't have to have snow for it to frost. All that has to happen is you have to take some gaseous water and cool it down until it's a solid without turning into a liquid first. And you get these water crystals. You get these solid crystals of water, and that's deposition. So our common word for deposition is frost. So frost happens when you go from a gas directly to a solid by removing some energy. So before I go, I'm almost to 20 minutes here, and that's pretty long. So before I go, let's talk about clouds. Between solid, liquid, and gas, what do you think clouds are? Maybe this is a good place to pause the video and take some guesses. Okay, so clouds. Clouds are one of two things on here. And if you guessed gas, you're wrong. Sorry. Clouds are not made of gaseous water. Gaseous water is actually invisible. We can't see gaseous water. We call it water vapor. There's water vapor in your classroom right now. You can't see it. So gaseous water is invisible. So that means clouds have to be liquid or solid. And in fact, they can be either. So whenever you see a cloud, it is either made of little raindrops, little droplets we call them, or it's made of little ice crystals. Now, if you're watching this video when it's cold out or in the wintertime, chances are very high that any clouds you see are made of lots of little tiny bits of ice. And if you're watching this video in the summertime, some of your lower clouds are made of little droplets of water. So now you might be thinking, how is that possible? How can a cloud be made of little droplets of water, and how come they don't fall? How come clouds don't fall? Well, the truth is that a big cloud can weigh more than 20 or 30 tons. But how big are the individual droplets? They are like thousandths of thousandths of a meter. They are tiny, thousandths of a centimeter. They're just tiny little droplets, and just a tiny little draft of air upward is enough to hold those tiny little droplets or ice crystals up in the air. So maybe some of you who have flown before have noticed that when you fly through the clouds, sometimes the windows on your airplane get wet, and that's the reason why. So the last thing I'll show you then is this image. So what's going on here? Obviously, right here, it looks like we've got a cloud. And what do we have right here? What do you see right there? Well, what you see right there is you see a whole lot of, it looks like nothing. But is it really nothing? Well, we know it can't be just nothing because look at this big daddy cloud here that's coming out of that stack. How can there be nothing right here? Well, the answer is it's not nothing right there. It's actually water vapor. And that's what we call gaseous water. So if you have water that is 100 degrees Celsius or above, then it is invisible and you can't see it. So now, why can we see the cloud here? Why can we look at this cloud? Well, as soon as it gets out of this nice hot smokestack, what happens to the temperature of the water vapor? Well, the temperature goes down and we move. Where do we move? Let me scroll back down here. When the temperature goes down from a gas, what can we get? We can get a liquid. We can get little droplets. And droplets are what clouds are made of. There you go.